We have studied the acids, we have identified which are the common acids. We've really focused on the oxo acids, trying to understand why is it, what factors intervene in weakening that bond with hydrogen that makes it an acid release that proton. Now we're going to try to understand why is it that some bases are basic. What makes a base have that lone pair typically that will make accept a proton so that it becomes protonated. Okay, so and therefore releases OH negative in solution. It's very important to understand, and at some point you may as well just need to memorize the three different kinds of bases that we will deal with. The amino groups is the first one, and the amino groups, ammonia is the simplest one, but notice that you can substitute a hydrogen with an alkyl group or any other organic group. So let's just write it like that. We said amino groups are not acid. This nitrogen-hydrogen bond is not weak enough for water to accept that proton. It actually behaves like a base. So if you have water, let's just draw it like that, this hydrogen will go into here and you will have the amino group being protonated. I'm writing the structure so that you understand why is it that amino groups are basic. And it's important to understand because it does not belong to the list of strong bases. Amino groups are typically weak bases. So every time we have an amino group reacting in water, there'll be a equilibrium constant, there'll be a back and forth, the distribution of reactants and products. It's not completely displaced to the right. The same goes for the carboxylate, and there's a spell mistake here. Carboxylate ion is the conjugate base of carboxylic acids, and because carboxylic acids are weak, it means that the conjugate base is also weak. Okay, and the acetate, for example, will react with water to form, and two arrows for indicate equilibrium, to form the acetic acid and OH negative. Okay, so yes, carboxylates are basic. And finally, it's important to memorize because the list is long, the oxoanions, which are the conjugate bases of oxoacids. Notice that some of the oxoacids are strong acids, and I'm going to write them here. Remember, perchlorate, and these are strong acid. That means that the conjugate base is neutral. So sulfate, these are not bases. So I'm writing them here so because you will not see any of these oxoanions in this list because these are neutral. They are not bases. Okay? The conjugate bases of weak oxoacids are bases. So carbonate will react with water to form, in first instance, hydrogen carbonate and OH negative, and so on and so forth. Needless to say that, as you already know, strong bases in which the group 1 mixes with group 1 or group 2 of the periodic table mixes with an hydroxide, that will be strong base. Let's comment a little bit about how we name oxoacids, in this case oxoanions, because they are the conjugate base of oxoacids. How do we name them? We name them the same way that we named the oxoacids, with a prefix and a suffix depending on the oxidation state of the central atom. Remember, if you can calculate the oxidation state of this central atom, it will in this case, when there's four possibilities, there is the IPO ITE for the lowest oxidation state, ITE for the second lowest oxidation state, ATE, in this case chlorate, for the second highest oxidation state, and just per ATE for the highest oxidation state. Notice that because these are the conjugate bases of strong acids, these are neutral. They are not bases. Why? Because perchlorate and chlorate are strong. And the conjugate bases of strong acids are neutral species. They are not basic. These, however, because their conjugate acids are, so you got the chlorous and hypochlorous acid. These are weak acids. That means that the conjugate bases will be weak bases as well. Okay. The same goes for, in this case, carbonate is the conjugate base of carbonic acid. This is carbonate, and notice that it's an amphoteric substance. So we will talk about amphoteric substance in the next section, but it's a multiprotic acid. So you have carbonate and hydrogen carbonate, and both of them are bases. Nitrate, notice that nitrate is the conjugate base of a strong acid. This guy is neutral. Nitrite, however, it is the conjugate base of a weak acid because it's not in the list of strong acids. It is a base. Phosphate, we can write more species. Phosphate, hydrogen phosphate, hydrogen phosphate, dihydrogen phosphate, okay? They are all bases. And phosphite, this would be, phosphite. Notice that the oxidation state of phosphorus in here is +5 and here is +3. Okay, this is why they have the different terminations, ITE or ATE. This is the same applies for phosphite, hydrogen phosphite, and dihydrogen phosphite. Okay, all of these are bases. They can accept protons. Sulfate. Sulfate is the conjugate base of a strong acid, therefore is neutral. And sulfite, the oxidation state on the sulfur is +4 if you count it, +4. This is sulfite or hydrogen sulfide. They both behave like bases. I want to point out, however, that the partially protonated species, if you think about it, it could either behave like bases or behave like acids. Let's talk a little bit more about that. And because those are called amphoteric substances. An amphoteric substance is a substance that can behave like an acid or behave like a base, as I'm reading, depending on the strength of another substance. What do I mean by that? So imagine if we were to identify the amphoteric substances of the partially deprotonated oxoacids, that means that hydrogen carbonate, if it behaves like a base, imagine for water, it could behave like a base and therefore transfer this. In this case, hydrogen carbonate is an amphoteric substance because in this case it's behaving like a base, but it can also behave like an, I'm sorry, in this case it's behaving like an acid because it's transferring the proton, and in this case it'll behave like a base. Okay, what does it depend? Which way is it gonna go? You would need to memorize which way it's gonna go. We will need to do some calculations to look at the equilibrium constants, which one is larger, but in general it depends on the character of the other partner, if it's willing to accept a proton or willing to accept or willing to deliver the proton. Let me give you an example. If hydrogen carbonate reacts with a strong base such as sodium hydroxide, it will for sure behave like an acid. So you will have something like that. Why? Because hydrogen carbonate, or also known as bicarbonate, can behave either as an acid or a base, but definitely sodium hydroxide can only be a base. So it forces onto the amphoteric substance to behave like an acid. Therefore, you'll have just here. And of course, to balance it properly, you need something like that. I apologize. No, that's not true. Yeah, we'll leave it like that. Okay. The same goes for hydrogen sulfite. Okay. These are also amphoteric, and also for phosphate, hydrogen phosphate. these can all be all these can be amphoteric substances. All these, depending on if it reacts with an acid or a base, can behave like an acid, like a base or an acid. Okay, and I think I'm leaving some. I'm just looking through the list. Yeah, I forgot these two. So let's make sure we understand also that the dihydrogen phosphite is also, these are all amphoteric substances because they can behave like an acid or a base. We will not ask you to predict when it behaves with water, which way is it going to go. However, when it reacts with a strong acid or a strong base, the strong character of that strong acid or strong base will force the amphoteric substance to behave at a specific with a specific outcome. For example, if I'll give the opposite, if bicarbonate, which is an amphoteric substance, reacts with hydrochloric acid, because hydrochloric acid is a strong acid, it means that in this case bicarbonate or hydrogen carbonate will behave like a base. Therefore, it will accept a proton, and here you have your chloride. And to further complicate things, carbonic acid actually decomposes into CO2 and water, and this, you may experience this when you burp, because the acid of your stomach is neutralized by the bicarbonate secreted in your stomach, and when you burp, it's actually the CO2 coming out as a result of this neutralization reaction.